Well, this lesson is for Algebra 2. It is 6.6. These slides are a little differently formatted, so I don't have the usual title. And these are on inverse functions. We've already studied these before, so a lot of this is going to be review. And we're going to determine whether the inverse of a function is a function, and we're going to write rules for the inverses. A one-to-one function is one in which every x is paired with exactly one y, and every y is matched with only one x. So one-to-one functions are they're always going to be either increasing or decreasing, like that or like this, for instance. They can't go like that because, in this case, this y value would be paired with 3 x's. So to check to see if it's one-to-one, we use a horizontal line test, because you can see this, if I drew a horizontal line, this function would cross it more than once, and that means it would fail the horizontal line test. So the horizontal line test checks to see if a function is one-to-one. Let's see, we'll make some room here. Oh, here. So check out this one. If I draw a horizontal line, it crosses at most once. Same here. Anywhere I cross, it's only going to cross once. So we'll clear this off a little bit so we can write the definition for one-to-one. Or the horizontal line test, that's what I wanted to do actually, because it tests to see if it's one-to-one. Horizontal line test. A horizontal line will cross a one-to-one function at most once. And when that happens, if it is one-to-one, then the inverse will also be a function. It will say if f of x is one-to-one, then its inverse is a function. That's why we care about this. That's why we care whether it's one-to-one, because it tells us whether the inverse is a function, and we're obviously studying inverses. So horizontal line test will test to see if it's one-to-one. If it's one-to-one, then the inverse is a function. If it's not one-to-one, it can still have an inverse, but the inverse just won't be a function. And visually I could show you that too. Like, let me pick one that's not, you're not going to be able to see that very well. Let's pick one that is not one-to-one. How about a parabola? So you can see if I drew the horizontal line, it would fail because it would cross more than once. Then remember that inverse or functions and their inverses are reflections over the line y equals x. Remember the y equals eggs, that joke? So if I reflect this purple parabola, this maroon parabola, over that y equals x line, I will get this green one that will look like that. And is that a function? Is that green curve a function? No, because it fails the vertical line test. So see, this parabola, which is not one-to-one, its inverse is not a function. However, the inverse does exist. It's just not a function. And mathematicians like functions. So that's why it's important, right? Discuss inverse functions and the horizontal line test. Already did it. Moving on. What do we got here? If a horizontal line... Okay, so I just talked about this. Well, underneath we probably have some pictures. Yes, it passes the horizontal line test. This one's not going to pass. So, oh, there's a parabola. Don't worry about writing this down. This just confirms what I just said. Use the horizontal line test to determine whether the inverse of the blue relation is a function. Okay, so if you look at the blue one and you use a horizontal line, is it ever going to cross it more than once? No. So the blue one is a function. Or actually it's one-to-one, so it's actually not a function, is it? The blue one itself is not a function. It fails the vertical line test. But the blue one is one-to-one. So its inverse will be a function. Now on the red one, it's a function. It passes the vertical line test, but it fails the horizontal line test. So the red one is not one-to-one. So its inverse is not a function. Okay, so writing's sloppy as usual. Oh, we already did that. See, I'm anticipating. I know what this is all about. Use the horizontal line test to determine whether the inverse of each one is a function. Does it pass the horizontal line test? Yes. Now this one happens to be both a function itself, because it passes the vertical line test, if you draw these vertical lines. It also passes the horizontal line test. So it's both a function and its inverse is a function. Writing inverse functions and comparing domain and range of a function and its inverse. Okay, I'm not sure what I had in mind. I made these slides last year. Not too sure what I had in mind for that one. Let's do the example and see. Find the inverse of that function and then determine whether it's a function and then state the domain and range. All right. So I'm going to first of all write this as y equals, just rewriting it. And then you probably recall in the past when we wanted to find the inverse, we switched the x and y. So this is now x and the x is now a y. And then you solve for the new y. So we undo a cube root by cubing. So I get x cubed equals the cube undoes the cube root. We're left with just the y plus 1. And then we subtract the 1. And we write the y as y inverse. Remember y to the negative 1. Actually, I kind of paused for a minute because you only write that if indeed this is a function. Is x cubed minus 1 a function? Well, you can tell a couple ways. I mean, if you know what it looks like, you should know what it looks like, right? It's y equals x cubed, move down 1. You could just directly do the vertical line test on this equation itself and see that yes, it passes the vertical line test. Or you could have taken the original equation up here and done the horizontal line test, which would tell you whether that's inverse, which is this, whether or not it's a function. And then this one too, you should remember what that looks like. A cube root has this shape like that, and then this is just to the left 1. Does that pass the horizontal line test? Yes. So yes, it is a function, so we can use y to the negative 1. I will box this in because this is one of our answers. So yes, it's a function. And then it asks for the domain and the range. Now, there's a couple ways you could do it. You could do the domain and range of the original function and then swap them, like the domain becomes the range and the range becomes the domain. Or you could do the domain and range directly from this function since we know what it looks like. I think just for purposes of illustration, I'll do it, let's do the original f of x, its domain and range, just so you can see how this works. Of course, you already know, if you remember. And then f inverse, its domain and range. So I already used transformations, and I already have an idea what this looks like. So this one's f. Its domain, as you can see, is going to go on and on forever. There's no breaks, so it's all reals. Hey, the range is too, because it's going to go down forever, it's going to go up forever, so it's also all reals. Well, this one is hardly exciting because obviously this is also going to be, and you can see it here, domain and range are both all reals. Fancy R's. Okay, try this one on your own, and then I will state the answers. Do I even have them? Tell you what, I have them somewhere in this classroom. I think I wrote them down. Okay, here are the answers. Y inverse, or I'll write it correctly, f inverse, is going to be the cube root of x plus 2. That's after you switch the x and y's and you solve. And then the domain on the original one is all reals, as is the range. So the domain and range for both f and f inverse are all reals. That one's pretty similar to the other one we just did. Cube root and cubes. Okay, so this sounds like something I've already talked about. Functions that pass the horizontal line test are one-to-one. For one-to-one functions, each y value is paired with exactly one x. Okay. Oh, now we get to do something new. We can verify that two functions are inverses of each other by using compositions. So this is totally new. If you have f and g, and you compose and you do f of g, and that equals x, and this has to be both, and g of f of x also equals x, they both have to be true, then f and g are inverses. So that's a new way to test to see if two functions are inverses. Compose them both ways, and if you get x both times, then you have inverses. So that's just what I said there. Let's move on, and let's do an example. We're going to determine by composition whether these are inverses. So we're going to do f of g and g of f. So here's f of g over here, and over here's g of f. And I'm going to be checking work on these, so make sure you go through the steps. So f of g, you take the inner function, which is g, and you put it into f. So this whole thing will be going in for x. So I'll have a 3. I have to replace the x, so I need a parenthesis. I'm replacing it with this entire function, 1/3 x plus 1, and then minus 1. And then let's do the math. So we're going to distribute the 3. So that's going to be 3 times a third, which is x, and then 3 times 1 is plus 3, and then minus 1. Oh, that's not going to be x. X plus 2. So I already know that they're not inverses because this one doesn't equal x. So they're not inverses. That's funny. I kind of thought they would be. I was expecting, oh, it's going to be an example they're going to be, but nope, they're not. Let's see if this one is. So let's try it again. So let's do f of g. So I take all of g and put it in for f. So I'm going to have 2/3. I'm going to be replacing that x with all of g, which has to be in parentheses, plus 6. So I'm going to distribute my 2/3. That's going to be 1, so just x. 2/3 times 9, you could put that over 1. 3 will go into 9 3 times. So then I'll have 3 times 2, which is going to be -6, because I have a positive times a negative. If you don't like that, you can do that over here on the side. Or you could get -18 over 3, which is also -6. Oh, this one. I see all the steps in the work. We have g of f. You can't just assume that because one of them equals x, they both will. So now I'm going to take all of f and plug it in for g. So I'm going to have g equals 3/2. Replace this x with all of this. 2/3 x plus 6. Close the parenthesis and then bring along the -9. Again, I'm distributing. Two-thirds over 1. 2 goes into 6 times 3, 9. And they're both positives. And then -9. Aha! We've got an x out of that one as well. So they are composite. They are inverses. Oh my gosh, we're done? Because this is my little lesson. I can't believe we're done already. Well, that was one fast lesson, wasn't it? Okay, well, we'll see you in class.